let's continue. My throat's a bit hoarse today, so I'll use this a bit more than normal. So let's recall what we were looking at last time. We had this algorithm for checking if there is an element in an array, or rather, we have an algorithm that given an input where you promise to have one item that occurs more than half of the time, using only one or two extra words of storage, right? And I think I gave you the solution, and I said, this is the answer, and we tried the example, and it kind of worked. But we didn't really reason about why this works, right? And I want to do that because I'm going to use that as the basis for a more general algorithm that allows you to find not just the one element that occurs half the time, but elements that occur very often, whatever very often means. So again, let's recall the algorithm. So again, it'll be easier just to draw it pictorially rather than to give the whole detailed algorithm, because I'll probably make some mistakes and I'll just call it over. So, okay. No.
Does this problem or algorithm have a name?
It will in a second, once I figure out why my thing is not working. I all got the trouble. That's not it. Oh, come on. Okay, this is going to be interesting and not much fun. Sorry, other than just turning on, turning off again, I really have no idea what's going on. Not the best solution to any problem. All right, let me see if I can. This is going to be a little weirder. I will try to do it just using my touchpad. Okay. So, the idea was that we'd have two. It's terrible. So I apologize. So we're going to have 2 units of storage, and the number is going to come in.
Would that pen work on it?
No, the pen is designed only for this. And I'm afraid to, hold on. Give me 2 minutes. If it doesn't work in 2 minutes, we'll do triage, but for now, let me just write it. The name of the algorithm is, actually I don't know the name of the algorithm. Think about it, 2 minutes. I don't think it has a name for it.
Sequence frequency?
Frequent frequency.
Not that one. The later one has a name. But this one doesn't. The simple majority one doesn't have a name. So anyway. Good. Okay, so my tablet is working, my pen is not working. So I could write my finger, which is a little bit better than trying to write on the touchpad. But it's still not going to be great. Should I? Okay, let me see if I can use the board today. I know it's not ideal for people in the back, so maybe if you all could move forward a little bit, we could try doing that. Sorry? You mean the back button?
I don't think it's not. If you use non-narrator, it will work.
It will?
At least work.
Well, I tried this. Ah, thanks. Sure. No. No. All right, so if you all, the people in the back, you come up front. We'll use the board and I'll try to write hard. I know it's a little bit awkward. But yeah.
So you can use this from a phone.
Yeah, from your phone.
You think it'll work? Oh, it's an Android, it might work. Because the iPad, things are different. No. Thank goodness for proprietary technology. Who cares what interoperability is? All right. Let me remember my board sequences. All right, so again, apologies for the last minute version. But, life is all about adaptability, so we'll adapt. So we are talking about the majority algorithm, and as I said, if you recall, you have two things here, right? You keep the label and you keep the count, and then when the items stream in, so let's say my item sequence was, I don't know what it was last time, 1, 2, 1, 1, 7. Let's keep something simple like this. So there are 5 items. The 1 occurs more than half the time, so this is an acceptable input, which I expect to get the answer 1. So I see my input 1, so I have 1 and the count is 1. I see the input 2, so I threw out the 1 I had before. Its label is not 2, and I replace it by the label 2 with the count of 1. Then I see the 1 again, and again I replace it back to 1 with the count of 1. I see the 1 again, I can call it 1 with a count of 2. I see the 7, so I subtract a count, but it still says 1 and 1. At the end I return 1, and lo and behold it's 4. Right? So this is the algorithm, and the question is, why does this actually work? And why it works is kind of interesting, right? Because remember the promise here, that there's one element that occurs strictly more than half the time. Okay, not half, strictly more than half. Okay? So imagine you're trying to keep track of the count of this element. Right? So let's say you're not, imagine the proof and you're keeping track of the count of this element, you want to see where it's going to actually show up. So so if you think of it, let's say its count is measured along the y-axis, right? So this is 0. So it starts out at 0 and then you see it at some point. But the first time you see it, what's going to happen? The first time you see the element that actually is the majority element.
So the graph is going to move up.
Well, it will move up or it may move down. It might decrease what's already there, right?
Okay.
Right? So let's pretend for now that it is in fact the first element of the list. We'll worry about what came before, because if you can prove it if it's the first element and it's always correct, we'll say what happens if something is before. So let's say the first element of the list. So it gets a count of 1, right? So we'll just draw it here as a count of 1. That's the first time step here. Okay? And then maybe another 1 comes along, and so at next step it becomes a 2, right? It goes up there. And then something comes along that's not a 1, so it comes back down to 1 again. And maybe something again comes, it's not a 1, so it comes back down again. Right? Now nothing happens for a while. Right? Then it shows up. Right? So it shows up again, and maybe there's some other counter there. Some other stuff has happened in the meantime. And now this count of the 1 brings it down by a bit. Right? And maybe the 1 shows up again after a while, and it brings the count again down by a bit. And so on and so forth. So here's what you can see, right? Every time there's a 1 going up, or rather every time the 1 goes down, there's a corresponding other element that went up to match it. It's always. Right? So there's always a matching thing here. There's 1 up here, 1 up here, 1 up here, 1 up here. There's always a match. Right? So if you look at the most frequent element and you write down all the little tick marks corresponding to when it shows up, there's always some other element you can match to cancel it back down. Right? But remember what we said about this element. It occurs strictly more than half the time. So after all the matching has been done, it's got a couple of things left. And there can only be one element like this, right? You can't have more than two. You can't have 2 elements that both occur strictly more than half the time. There's only one element that's special this way. That it can be matched up with everything else and still has something left over. Everything else gets nuked out. So in other words, the total count of this element is whatever it is. Let's say the count of this element, f max, is some number f max, which we know is more than n over 2. This is what we know. We promised this. We also know that the number of times it gets decreased, right, is at most the total number of other elements in the set. Because every other element has the opportunity to remove it just one time. So the number of times it gets decreased is the number of remaining elements in the set. Okay? And so the final count you will see of this element, so the final count which we'll call f hat, is equal to is equal to f max. Right? Well, let's just say it's greater than equal to f max minus n minus f max. Okay? And also, obviously, this count is less than equal to f max itself, right? So the approximate count of this element is less than the true count, because there are some times when you don't actually count it, because it gets subtracted. But it's always more than this minus that. What does this thing remind you of, this statement here? When I talk about approximations, what is the most important thing you need to worry about? Yes, error, but how do we reason about error? By giving upper and lower, by giving lower bounds, exactly. Now for a minimization problem, we only worry about the lower bound. In general here, we're trying to, in some sense, we're trying to get as close to the true answer as possible. So we know it never gets larger than the true answer, but we know it never gets too small. Okay? Yes?
Can you move your laptop just a little bit?
I could.
Really?
In fact, move my laptop a little bit. And that's where this guarantee came in, by the way. This guarantee isn't sort of, it doesn't come by magic, it comes by this reasoning. What I want to say is that the ultimate count of the element I'm looking for is more than 0. If it's guaranteed to be more than 0, and I only have one storage item, I'm going to get it. How do I make sure this number is more than 0? By making sure that 2f max minus n is more than 0. Solve for that, get this guarantee right here. So it's not surprising that we need this guarantee, because this guarantee is what makes the argument work. Notice that if the element was exactly half, this could become 0. In which case, you can no longer guarantee that element will show up. So that's the algorithm, the trick question that you potentially be asked to do. This is the reason why it actually works, which in my mind is more important. Yes.
Can we understand in a way that since the number is occurring more than half of the times, then there has to be a place where it's occurring consecutively, and that's what we mean.
Is that enough? So suppose there's a place where it's occurring consecutively. But suppose that consecutive occurrence appears right in the beginning. Okay? So let's say my number was 1. So in my list, I see a 1 here, I see a 1 here, and now I see a 2, and now I see a 7. It will still remove all those 1s. Just because they occur consecutively doesn't mean they will stay, you'll stay at that higher level. What you then have to reason as well, in this case, essentially these will cancel this, but there's still going to be some leftover somewhere else. I mean, this pair of 1s is not important in some sense. There's going to be somewhere else where this happens again, because you need that. So, while your intuition is correct, it doesn't lead you by itself to the correct answer. You need to do it slightly. So in some sense, what we're doing here is a generalization of what you're saying. Rather than saying there's always 2, you're saying on aggregate, there's going to be a discrepancy. Right? So it's in the right track, it's just not, yeah.
It sounds like pigeonhole.
It sounds like pigeonhole. In a sense it is, right? Because, how am I typically like a pigeon?
Because always there are less number of holes, more pigeons, one hole.
Yeah, but I'm trying to, I mean, this is a good, if you want to get a nice warm fuzzy feeling in your stomach, then this is a good way to do it. And I highly recommend warm fuzzy feelings in your stomach for proofs. But they're not proofs. You have to convert that into a reasoned argument. And I'm trying to see how to convert that. Yeah, so. Well, what are the pigeons here?
The numbers, but then the
And what are the
holes have
holes?
to be.
Yeah, what are the holes?
Yeah.
You want something
You're
like,
actually storing only one element.
that's the problem.
Yeah.
So the intuition is not bad, but yeah, I don't know how to map it to an actual thing.
Can you tell me what the equation I can't see?
So, sorry. Yeah. F hat is greater than equal to F max minus N minus F max. Because the number of decrements you can get on this counter is everything else.
Oh, you're taking the worst case. Worst case.
That's why it's greater than equal to
Makes
it.
sense.
Okay, it's a worst case scenario. Yeah. The worst case scenario is basically a complete alternation. Right? And then at the end you get 1 extra.
But you didn't prove that it's worst case because it might not be F max minus N minus F max, right?
It could be better. This is a lower bound. I'm saying it's at least that much.
No, the worst case is N minus F max, that is true.
No, yeah, that's right.
But not F max, because I could have some. I mean, you did not prove the F max, right?
Why? Because you know, if I don't decrement, I get the actual count. Any discrepancy from the actual true count F max comes from people subtracting away.
Other people have that.
Right.
Okay. Yeah.
So that's why I would get this if not for those pesky other items in the list that I just don't like. Any other questions? Okay. Again, it's like this is the warm up to the main act, right? So make sure you understand this. We're going to use some generalized. Yes.
Could you explain F hat again? It's representing the final value.
F hat is the final reported count of the item that was promised to us as being very frequent. F hat could be 0, in which case we would report it. But we want to know what F hat is. And we're saying, okay, let's try to estimate F hat. We know it's between the true value, if nothing ever got subtracted, and the true value minus some stuff. By assumption that the stuff is not a lot of stuff. And so if we can guarantee that the reported value is at least 1, and we only had 1 unit of storage, then that's the one we're going to report.
And we know that the final label has to be that maximal element.
Well, the label corresponds to the element who's currently active.
Right. And we know
So-
that at the end of the round.
This
that-
one element is active,
Okay, that has
because its count is more than 1.
right.
Because whenever you get an element whose count is 1 or more, you put its label into the mix. And you can put it as a new element, or you're subtracting from a higher value, but you keep its label. The only time you change the label is when you throw this element out, and you think its current count is 0, you put something else.
Okay.
Right? That's a good question. All good? Yes.
And you still have to have the guarantee that there is some element greater than n over 2 in
Right,
frequency.
because I can't, otherwise I can't guarantee this exactly. So if I give you, so if I give you an equal number of 1s and other things, all bets are off. Maybe my answer will be 1, maybe it won't, depends on the ordering. Right? If I had the ordering where it was 1 something, 1 something, 1 something, then the something will live at the end. If I had the ordering where it was something, 1 something, 1 something, 1, then the 1 will live at the end. But I can't say anything specific about it. It could be. Okay. the algorithm that this is a warm-up for, which is called the Mishra-Breeze estimator after the people who first proposed it. And the purpose of this estimator is to find out frequent items in a set. So the setting is now a generalized version of the setting. In this setting, we had one item that was very, very frequent, amazingly frequent. And so we want to find it. In general, we have a bunch of items. And there are some items that we believe are extremely frequent. And we'd like to find those. So I'm not exactly saying I want the most frequent items. I'm saying that I want items that are very frequent. Similarly here, I didn't say I want the most popular item. I want the item that has a large popularity. Okay? These items are called in the business, they're called heavy hitters, because they sort of punch you with the way they're very heavy. They're important. And as you can imagine, if you're doing any kind of data analysis, it's very useful to find these items because they capture, in any kind of heavy tail distribution, they capture a large fraction of the action in the data. And if you can identify a small number of items that have a lot of outsized importance, you can model your problems appropriately. So it's a very important problem to find these so-called heavy hitters. And so the way we're going to generalize this basic technique is to say, well, what happens if I'm allowed more than one block of storage? So think of this as a single block of storage, right? A label and a count. Suppose I have more labels and more counts. I should be able to keep track of more items. In that case, are my errors going to get even better? So in particular, think of the same algorithm as a similar setup as before. I have a bunch of items coming one by one, and I have this small amount of storage. Instead of one now, let's say I have k blocks. So I have so there are k of these things, right? And here I put a label and a count, because I want to keep track of the item and its frequency. And so every item I'm going to report some frequency, which is going to be some approximation of its true frequency. And my algorithm is going to be very similar to the one before. When I see an item, is there an empty spot in the list? Well, I put it in and give it a count of 1. Okay? So at some point I fill up all the items, right? So I say the first k distinct items, and then I fill up the whole array with all the first k. So maybe at some point I have a 1 here and its count is 5, and I have a 2 here and its count is 1, here its count is 2, a 4 here its count is 3, and a 5 here its count is 1. Okay? Now item label 6 shows up. Okay? I would like to put it in this array, but I can't. There's no room. So just like before, instead of putting 6 in, I'm going to subtract 1 from the counts of all of these elements. Okay? So this is going to become a 4, this is going to become a 0, this is going to become a 1, this is going to become a 2, and this is going to become a 0. Just like before, when I see a count of 0, I'm going to pitch it. So I'm going to throw out the 2, I'm going to throw out the 5. Okay? And so, put the 6 in here. So what's going to happen in my new array? Right? It's going to look like 1, 4, 3, 1, 4, 2, and I have 2 empty slots. Now I put the 6. Put the 6 in. And I continue.
If there's no empty slot, I just let it be.
If there's no empty slot, the 6 just goes away. Yeah, correct, good. So if none of these had gone to 0, I just throw out the 6. Just like before, if my count of 1s had racked up really high, new element came in and just dropped by 1, I just pitched the element up by dropping. At the end, I report the items in my set, the labels, and the frequencies. Okay? And what I'd like to do is understand how good these answers are. Okay? Any questions?
Say again, what happened finally?
At the end, when I finish processing all the input, I have some array with some numbers in it. Right? I just give all these are my answers for the most frequent items. And these are all the counts. Is the algorithm clear? So once again, we'd like to understand how good these frequencies are in relation to the true frequencies. Okay? And so let's think of the frequency of any item in the set. Again, as usual, if it doesn't show up in the final set, that means its answer was 0. But let's think of any item in the set. And let's think of frequency fj. Okay? And compared to the reported value, which could either be 0 or one of these things, versus f hat j. Okay? We are trying to understand these things. So I'm going to move over now to this board here. So what can we say about these quantities? So as before, we know that you can never exceed the true frequency count. You can't manufacture counts out of nothing. So we know for a fact that fj hat is less than or equal to fj. Just like before. That's the easy step. So the danger with this chalk, it will not erase.
Yeah, well, I used it when I did mine.
It works?
Yeah. The yellow is particularly readable.
It's readable, but it doesn't erase.
Yeah.
Usually the
That's
case,
why I have a board.
huh?
That's why I have a lot of board.
It's usually the case that they have chalk on the floor.
I'm just not in the drawer.
Sorry?
In the drawer.
Ah, yes. Okay, so that part is fine. But the interesting question, of course, is the rest of it. How low can it go, right? And that's what we want to say. We want to say that fj hat is greater than or equal to something involving fj. We don't know what that something is. So we think it's going to be
Minus n minus.
try to use a similar reasoning as we did before, but of course generalize it.
Will be greater than n minus not of it. Basically, n minus everything. Right? Will be greater than n minus j.
N minus fj.
Yeah.
So if fj is 1,
Yes, sorry. It's up.
so think of it this way now. There are many more opportunities not to subtract something. Because imagine at some point I have this area, right? And I see suppose I'm tracking the value of 4. So I'm looking at F4. And I see 3. In that case, I would have subtracted the count of 4 because 4 is now 3. But here, I can just increment the count of 3. I don't touch 4 at all. 4 stays unaffected. So because I have more space, and this kind of makes sense, I have more opportunities to keep my count safe and not have it be decremented.
I don't know if this is correct, but would it be fj minus n minus the sum of the frequencies that appear in the group?
That will be fj, like again be n.
Sort of. It'll be sort of like that. But it'll be even less than, even better than that. Because remember, there are k elements in the set. So it's only a kth fraction of these things will actually affect the count of this element here. So in fact, what you can say is that this count is going to be greater than equal to, I believe it's slightly bit wrong than what you said. It's going to be greater than equal to fj minus n over k.
I can also put n minus fj by k, right?
Baby steps. Let's first understand this. This is a weaker bump. That's not a weaker bump. This one I think would be enough for what we need. So the argument is that every new update, right, will either increment one of these things, or if it misses all of them, will cause a decrement, right? And you can't decrement everything. So all those the m possible updates that will happen, only m over k of them will affect any one of these things. And I'm not assuming any distribution anymore. It doesn't matter. Because the updates spread over all. And they're not, essentially because I have so many items, I have k items already in my set, there's just not enough items left to decrement any one of these. Okay?
Can we put a little bit lighter bound so that it makes more sense?
A lighter bound.
Like instead of n, if we put n minus fj, it's actually not tighter. It's
So in fact, if you can make this bound even better, and this goes back to what Charles was saying, basically n minus the sum of the frequencies of the items in the set. Let's say I belongs to the set fi hat. This is an even stronger bound because I'm subtracting a lot less. I didn't want to get into that right now. I can refine that bound.
no, it shouldn't be summation, right? It should be fj. Because it's
No, because any of those counts will not affect this count, right? Because they're getting their increment. They're not going to cause any decrements to happen. The only thing that causes decrements to happen are items that are not in this set.
my answer is n minus summation of fj.
Yeah.
If j is not, fi where I is not equal to j will turn up to be fj.
No, because n is just the number of items in the set, total number of items. Oh. No, because see, this set is only of size k. It's not everything except that. There's a whole bunch of stuff that's neither in the set nor, yeah. But that's why I say this is why I don't want to get into this way. This just causes more confusion than it's worth. You can do this, and in fact, the notes I handed out, there's a way to sort of modify this. I think I believe it. But let's not worry about it for now. But the point is you get this bound here. Okay? And this bound here is very useful. Because what it says now is that if you look at items that occur, a reasonable, okay, so let me. So I have one free parameter here. I can choose the value of k. I can choose how many buckets I want to maintain. So let me choose the number of buckets, k, equal to 1 over epsilon. Where epsilon is thought of as a very small number. Okay? This is a constant number of buckets still. But it depends on this parameter, noise parameter, the error parameter epsilon. If I now substitute this here, what I'm saying is that now f hat, the final count for any item, is of course less than or equal to the true count, and is greater than or equal to the true count minus epsilon times n. Just by substitution. And then just by doing the subtraction again, what we're saying is that the difference between the true count and the approximate count, remember absolute error, is less than or equal to epsilon times n. Just by algebra, just by rearranging the algebra. So what we're saying is that if we choose k appropriately in this expression, we can get a direct approximation bound on the error of any particular frequency report. And this is an absolute error. If you think of these frequencies as reasonably large, and that's where we get to the heavy term. If you think of a frequency as reasonably large, if the frequency is more than some constant times n, then this you can divide by n here and get a relative error approximation. In other words, this difference, if the true frequency was 1, or let's say the true frequency was something like, 10, and the n was 100,000, this is not a very useful bound. Because I'm saying, the difference between my true frequency and the fake frequency is at most epsilon times 100,000. But if my true frequency is 10, my answer could be 0, and I'd still be using that bound. That's not interesting. What's interesting is if these frequencies are large, a sufficiently large fraction of n. So if fj, for example, is c times n. So let's say fj is equal to c times n is some constant c. Then we're saying that fj hat is at least c minus epsilon times n, which is not bad. It's within some epsilon percentage of the true answer. This is n over 100, and epsilon is let's say 1,000. Then this is like 99, 99 over 1000 will go. It's close. So that's why this method works if you have for capturing the large frequencies in the set, not the small ones. And in particular, any item that occurs less than n over k times, or less than epsilon n times, may not actually show up at all in my time, because I have no guarantee of the long. And if I tell you I wanted only items that occurred more than epsilon n times, how many buckets would I need? Well, if every item in my set that I'm interested in occurs more than epsilon n times, then it can be only 1 over epsilon of those items, because n divided by epsilon is 1 over epsilon. And that's so this kind of makes sense, right? If I keep 1 over epsilon buckets, then I expect to capture items that occur epsilon n over time, and nothing else. And that's kind of what it is. So this estimator and its relatives get used a lot again in data analysis, mainly because it allows you to, in a very small amount of space, constant space, right, independent of n, keep rough track of the frequencies of very frequently occurring items that we care about. So, and again, when you take the data mining class, you might cover next semester, you might cover some of these things and their friends in more detail. But this is an example of how to think about approximations. Yes?
How did you say this minus n that you little bit of
Okay, so the basic idea, I also want to check one thing for this, right? I somehow thought I just want to make sure I if I don't, I do it. Good. Okay. So think of what happens when you decrement the counter for this guy, the element you're looking at. So you're focusing on a particular element J. It's in your set maybe, and you're decrementing its counter. Okay? So it's in your area, you've got a counter. Along with a decremented counter for this, you're decrementing k other things. K minus some other things. Because you're going to decrement for everyone in the set. And there are n elements in your set. So that's why the way to think about this is that what I want to say was that this can only happen in over k times. I think they're looking for something a bit more than that. Let me think how to say this. Why do you want to have
You can take your best case and then see that like after k elements every time.
Sorry?
After k elements every time. you will have
No,
to
so
take-
I think we should go back to this analysis right here. So remember this analysis, we said every time I see a decrement, I can pair it with an element that showed up in the stream at some point. You remember that? I said this one, because this went down, something had to go up to make it go down. And so once I paired them up, there was some leftover and that was on the argument. Right? Similarly, every time you make, so if I have my array here, right, and there are k blocks in it, and I make some decrement, right? Every decrement takes off account of an element that had to have shown up earlier in order to be decremented now. Okay? So if you think of the entire list of n items, okay, the counts, so you can mark off an item if it contributed to an increased count in this area. So some of these items will contribute to counts in the area. Okay? If I now decrement one, I'm going to decrement one counter of all the elements. So I'm going to mark off a bunch of things here. Right? And now they're gone. But how many times can I do that? If at every step, the minute I go decrement, I'm decrementing k of these things. How many times can I ever make a decrement? N over k times. Because each one is going to destroy k of the elements. Here, they was destroying one other element. One decrement changed, was mapped to one other element that came up earlier in the set. Because remember, once you go to the 0, you don't count it anymore. That's the point. Right? So you can associate every decrement with touching k elements that appeared originally in the list. So after you've done n over k of these things, there are no elements left in the list. So just by a sort of a counting argument, this can only happen n over k times. So it's kind of a backwards kind of, it's kind of like one of these greedy algorithm type arguments. So you make only so much progress because in each step you do certain amounts of work. And that's where you get over k.
And how do you fix k equals to 1 epsilon?
I decide. So I don't have to fix k to be anything. What I'm saying is, okay, I have this bound. What I really like is a bound like this, because this is an approximation bound. What value of k do I need in order to get this? Stare at this for a while and say, oh yeah, I put k equal to epsilon. So k is a reverse engineered value based on what I can prove about the algorithm and what I want from the algorithm. That make sense?
So for approximation algorithms, like
It's what usually happens, yeah.
okay.
Yeah.
So you decide first like how much error bound you want
Yes.
to get your result.
Yes.
And accordingly you decide something.
That's typically what happens. I mean, there are other versions where, I only have a certain budget. I have to only spend this much resources. What kind of approximation can I get for a fixed amount of resources? So for example, in data analysis, there's a technique called PCA for reducing the dimensionality of a large data set of high dimensions. And there you say, well, I have to plot it on a screen. I need 2 or 3 dimensions. What's the best error I can get for mapping my data into 3 dimensions? That's one side. The dual version of that is, no, I care about the error. That's what I really care about because I'm doing some analysis later that needs this much error. How many dimensions do I need in order to match it? So that you can think of the problem either way. So we'll look at approximations where we fix the error, and we'll look at approximations where we fix the resources. Okay, let's move on.
I have one question about this.
Yes.
I just didn't catch it earlier. Which bit do you choose to decrement?
You choose the decrement column,
What?
all the bits. If an item shows up that's not in your set, you use it to decrement all of them. That's the trick. That's why this whole analysis works. If you decrement only one, then this would be a much worse approximation, and you wouldn't even know which one to do. I mean, you could imagine picking a bin at random to decrement. I don't know what would happen there. I haven't thought about that. Something to There's an expectation you might never see anything. Okay. So let's tabulate things we know. We know about approximations. We have the sense of an absolute approximation and relative approximation. We've seen one algorithm for a vertex cover where you can get what we call a 2 approximation, right? That means a bound that is within a relative approximation of factor of 2. Okay? We've seen an algorithm where you can get any approximation you want as long as you play with epsilon. I can make epsilon to be whatever I want. By the way, suppose I want epsilon to be, less than less than 1. I want all my frequencies to be exactly right. If I set epsilon equal to 1 over n here, I'll get all the differences to be at most 1, right? But then how many buckets do I need? And it's not entirely surprising that if I want to make it the counts exactly, I need n buckets. So this degrades gracefully in the right way. Okay? So we see a bound like this where you can say, I can get an epsilon, and I'll put it within quotes because it's not exactly the same as that, an epsilon approximation for any epsilon. And that's very important, right? I can tune the algorithm to work at any desired degree of precision. And that's a very powerful thing. In fact, this thing is so powerful, they're given a name. They're called approximation schemes. It's not a single algorithm. It's really a family of algorithms. Why? Because you can think of this as saying, I have to fix epsilon first. You give me epsilon, I will give you the algorithm. If you change epsilon in the middle of the algorithm, I don't know what to do. So you can think of this as one algorithm for every value of epsilon. So this kind of algorithm is called an approximation scheme. That was just a single fixed algorithm. This is, of course, the gold standard. If you can't solve the problem exactly, this is what you want. You want to be able to get it arbitrarily close. This is okay, not so great. Okay. You can't get arbitrarily close, but at least I can tell you how far I can get. Right? And maybe if I worked hard, I could do better, but it turns out you can't. You don't know how to do any better. And in fact, well, I'm sure we'll talk about it. There is a third kind, which is even worse than this. It's not arbitrarily good. It's not even a constant. It gets worse as your input size gets bigger. So the approximation is some function of it. So I want to do one example back today because it's a problem where, again, you actually can't do anything better. It's a very common problem you come across all the time. And it's a very simple algorithm which you will invent yourself if you think about it for 5 minutes. And it actually works. So before I go on, understand the differences. Here I can get arbitrarily good approximations that depend only on the error parameter. The running time will of course depend on the error parameter as well. Here I'm going to get a fixed approximation. It's a constant. That means it's independent of the input size. Here I can't even do that. I'm going to get an approximation that grows as the input grows. So it gets worse and worse. But hopefully it doesn't grow too fast. And the problem I'm going to look at is the problem called set curve. Yes, sorry.
Here, our algorithm wasn't dependent on epsilon, right?
Wasn't dependent. Well, it is, right? Because no, in terms of that, I don't have to know what k is. I have to decide how many buckets to fix at the beginning of the algorithm.
Yeah, but
That depends on epsilon. Right? If I want a particular guarantee, I need to know upfront how many buckets to choose.
yeah, but just the number of bucks you have, not the ambiguity.
If you just say number of buckets you have, well, that's part of the algorithm. Step 1 of the algorithm, initialize an array of size. So it's something that is, right? If tomorrow, think of this way, in the middle of this algorithm, if you suddenly change epsilon, I would have to do something. If you didn't have to do anything, then yes, the algorithm does not depend on epsilon, but this one does, because now I have to change my guarantees. I have to add more buckets. Okay, so the set cover problem is a generalization in some ways of vertex cover. In the fall and the input, oh wait, have you seen set? Did we? No, we did unique set, which is a two. Okay. So I have a universe, which you can think of as set 1 through n. And I'm given a collection of sets, S1 up to Sn. These are all subsets of the universe. And the goal is to find a sub-collection, which means take a few of these sets. Okay, so let's call this Si1 up to Sik, which just means I take some collection of these sets such that their union is equal to the universe. So in other words, find a small collection of sets and covers it. Now this is the same as vertex cover, or this is a generalized version of vertex cover. Why is that? Think of my universe, the things I want to cover as, what do you want to cover in vertex cover? What do you cover in the vertex cover? The name is carefully chosen to confuse maximally. In vertex cover, you cover the edges. I know it's horrible, but so the universe here should be edges. We're trying to construct a reduction from vertex cover to this problem. So we take a vertex cover instance and we say our universe is going to be all the edges. What are the sets going to be?
Set of vertices.
Sorry, set of vertices. What did you say?
I was saying adjacent edges to a vertex.
Adjacent edges to a vertex. What else? So yes, in fact, that's correct. Each set is the things you can cover with one object. The object is a vertex, so that's a set of all the edges you can cover with it. So there, you just have a reduction on the fly in class and inferior dispersion. So you have your reduction consists of a vertex cover instance. You say that your universe is a set of edges. Your sets are the set of edges around any particular vertex. So you write them all out. And if you find a sub-collection here, you can easily see this is going to be a vertex cover. This you can do. If and only if blah blah blah. Linear time reduction. So this is NPR, right? But we still want to solve it. I'm going to stop this before. So what should we do? How do you find A? So I should say K is minimized. Otherwise it's easy. Just take care of it. I want to find the smallest cover. So I gave him an algorithm for which is a two approximation of vertex cover, right? It said take an edge and take both its endpoints. That would give you two approximations. What would the corresponding argument here be? If you had to translate that vertex cover approximation into a set cover, what would happen? So take an edge and take the two vertices around it. Here corresponds to take an element, because the element is an edge, and take all the vertices that touch that element, all the sets that touch that element. Then you can, and if, check if anything's left to be covered. If there is one, take it and take everything covers it. Okay. We showed that this was a two approximation basically because there were two vertices touching a particular edge. That's roughly speaking why the approximation works. There are two vertices touching a particular edge, and therefore you get a two approximation. Here, if you say take a edge, which is an element here, and take all the sets covering it, there could be many, many sets covering it. And that would be approximation guarantee. It would be something like n. It should be terrible. We don't want that. So the vertex cover idea doesn't work here. That simple algorithm doesn't work. We need something else. What could we do? So again, I'm going to encourage bad habits. What would be a bad habit here, a bad thing to do here as an algorithm? What's the worst possible thing you could do? Come on, the greedy algorithm. What is the greedy algorithm? Yes?
Just find the subset with the largest number of elements.
Very good. Find a subset that covers the most number of uncovered elements. In the beginning, of course, everything's uncovered, so it's just the largest number. Take it, and then remove everything that covers. Then repeat. Okay? So the greedy algorithm. So the greedy algorithm for this is pick the set that covers the most uncovered elements. Repeat. That's it. Very simple algorithm, it is greedy. And I wish that we are making a local decision. How well does this do? This is the question you want to ask. How well does this algorithm actually do? So this turns out to be a very interesting and not trivial algorithm. Not trivial algorithm to analyze. The algorithm itself is very interesting. But you will find this algorithm show up and this problem show up in so many different places that it's very good to remember that this one actually does something. To give you the punchline before the joke, we will show that this gives you a log n approximation. That means that whatever the optimal solution is, your solution will be at most that solution size times log n. So if the optimal solution was to cover the entire thing in one set, I will give you log n sets, which is quite bad, think about it. Especially as n is log n. But we will live with that. Turns out you can't do any better. None of us easy with it. So this is the thing we want to get to. So let's try to understand how. Okay? Alright. So in order to understand what's going on in this algorithm, it is helpful to add some extra information to what's happening, which won't affect the algorithm, but will help us keep track of some bookkeeping to understand what's happening. And so, let's imagine that at some point in the algorithm, we have some R elements that remain uncovered. So initially, we have R is equal to U, and as time goes on, we reduce the set down to some smaller size. At the end, you want R to be empty, that everything is covered. And let us also say that what would we like to do? We'd like to get a set that covers as many of these as possible. So if we think of a cost assigned to a set, right? We can think of a cost assigned to a set S as something like, at any stage in the algorithm, the cost of the set S is equal to 1 over S intersection R. Right? Because at this point, if this number is large, this number is small, and that's the one you want to pick. But so you're going to pick the element of minimum cost in this sense. Okay? All right? And what we're going to do is then, for all elements belonging to S, we're going to give each of them a cost. That's equal to this. We're going to assign a cost to each element. In some sense, this is the price of each element in the set. Its value is in that it's picking up this one, each element is picking up a 1 over fraction. That's its contribution to the entire proceedings in some sense. Okay. All right, that's okay. Hold on. Talk for a second. All right. So again, I'm not using these numbers. I'm just kind of adding some information to the algorithm. I'm not going to do it. So here's the first thing I want to say. Let's look at this. Let's say the solution produced by the greedy algorithm is the subcollection C. It's a collection of sets. Right? And now I add up for all the sets in this collection, I have number 1. This is a very fancy way of saying how many sets are in this collection. Right? I claim that this is equal to the sum of the values of the elements belong to the universe. So this is an important factor of motion. Okay, let me try to explain what's going on. So first of all, let me just explain why this is true. So each element that is, so I take a set and I use it to cover some set of the universe, right? And then I assign this value to each of the elements of that set. But notice that there are exactly these many elements that have not previously been assigned a cost, right? So if you think of S, let's think of S and R. So this is the set of elements that remain uncovered at any point in time. And this is my set S. Okay? These are the elements here. Okay? Now none of these elements, sorry, yes, none of these elements have been covered before. That's why I'm using them to cover. So they all get this label. And there are these many of these. All the elements in S that are not here have already been used to cover the universe before. They've been assigned a label sometime before this now. They haven't been assigned a label yet. And these elements we don't care about anymore. So all the elements that are assigned a label for the first time, this cost for the first time, there are exactly S intersection R. So if I add up the cost of all those elements, I get 1, corresponding to picking this set. And that's a proof of this. So you should think of these summations as happening in phases, right? Every time you assign a label for the first time, you look at this cost, you add up those numbers, like you choose 1. That's one set, then next set, then next set, then next set. Okay? So far I haven't done anything. I have not analyzed this algorithm at all. I'm just observing something about it. That I can express the total cost of the algorithm, the greedy value, in terms of these numbers here that I've created by thinking about it. The goal, of course, is to somehow show that this thing is related to what the optimal solution will look like. Because then I know this is what my solution looks like. If I can relate this to the optimal solution, I now have a connection between opt and might, and I'll be happy. And here's what I want to say. What I want to say is somehow that so I ran my algorithm with all these costs, I wrote down the numbers. Now all my elements of my universe have a number associated with them. This number here. And now I look at what the optimal algorithm did. It got some sets, it fixed some stuff. And I want to claim that no individual set of the optimal solution can take a large chunk of this total cost. If I can claim that, then the opt must do a lot of work to get coverage of the entire set. Because no single set of the optimal solution can pick up a lot of this cost. So it picks up a lot of sets. That's a lower bound. If I can say the opt is at least something, that's a lower bound, and that somehow is going to be useful. So that's the high level picture. That's what I want to do. Question is, how do we get there? Okay, yes?
You defined C of S first, which is for the set cost for that set, and then you went to the element cost.
Yes.
How are they equal? Because
They're not the element cost. No, this is just one.
No, the above that is equal.
I'm not saying anything's equal. I'm just saying, okay, let's just think about this.
So is for all E or what is that?
For all E belonging to, I should say, S intersection R.
S intersection R.
Yeah.
Cost of E
is going to be set. I'm going to define it. Sorry, I'm going to define it by fiat. I'm not saying it derived from anything. I just tell it.
Oh,
I'm constructing the cost.
Okay, you're making the
Yes. I'm defining the cost value to be that.
To be that.
Yeah. Yeah. So I'm creating it from no. Yeah. And then I say, oh look, I have this nice property. That if I now look at the cost of all the elements in my universe and add them up, that's equal to the size of my solution. By this proof. Because every time I add a set, I add a fractional amount. There are these many elements in the intersection, and it is corresponding to 1. So let's take an example here. So let's say I have the elements 1 up to 10. Okay. And then I'll say I have a set 1, 2, 3 that I pick. Okay. I pick 1, 2, 3. S intersection R is 3. So the first 3 elements get a cost of 1/3, 1/3, and 1/3. Okay? Now let's say the next set I pick is 4 up to 10, and also has 1 and also has 2. Okay? Now S intersection R is 7. So each of the new elements that I have not yet labeled before get a value of 1/7. Now I add those weights. 1/3 plus 1/3 plus 1/3 is 1. 1/7 plus 1/7 is 1. 1 plus 1 is 2. Oh wait, 2 sets. That's the statement. So sometimes the statement is trivial, it's by design. It's just that when you write it out that way, you can see what's going on. Okay? So now I have all these costs for these elements. Now forget about my sets. Just look at the cost of these elements. Every element now has a cost that my algorithm produced for it. Okay? Now I'm going to look at what the optimal solution does. Maybe the optimal solution picks some set 3, 7, 10. Right? So the cost for that would be 1/3 plus 1/7 plus 1/7. I have these numbers. What I want to claim is that the total value it can get in its own set can't be very big. It just can't. And so it has to take a lot of sets. And that's going to be good. So let me try to make the argument. So, okay. So let's fix any set of my input. Any set SP. Okay? So there's some set in my input. Let's look at any set. And let's look at the cost of the elements in this set. So the cost of the elements in this set is basically the sum over all elements belonging to SK, C of E. Okay? Just like I said, if you took the set at 3, 7, 10, I just added these values here. I want to give it an upper bound on this value. So I'm going to say this is less than or equal to. And let's say SK has size D. Okay? So this is going to be less than or equal to H. What is H of D? H of D is a harmonic function. H of D, H of N is equal to summation 1 over I going from 1 to n, which is roughly log n. Okay? This is a harmonic sum. So what I'm saying is that this number is really log n. Okay. For any set of input, because of the way I designed my algorithm, the weights that I'm going to assign to these elements will be such that this is always true. Okay. So suppose this is all. Suppose I'm not going to prove this just yet. Just hold on for a second and say, suppose this in fact is true, right? Then look at the optimal solution. What is the optimal solution? It's some collection of sets. I don't know what they are. It's some collection of sets, right? So it's going to be. So now if I look at the sum over all sets in the optimal solution, C star, the sum of all, for all elements belonging to S, S of CDE, right? This is going to be less than or equal to H, D, H, let's say max, SI times opt. Right? Because each one gives you that value, and there are opt many of these things. Right? If this is true, then this is true. But this is very important, right? Because we know that this basically is the sum of all E belonging to U, C of E, by construction. And this is equal to the algorithm cost from there. So we're saying the algorithm cost is less than or equal to this number times the algorithm cost. And that's the point. So in other words, what we got here was a lower bound of the optimal solution, constructed by using the weights defined by the algorithm. So if I were to prove the statement, which I may or may not do with the time, I'll get a bound now. And this then basically bound is going to be a log. Maximum size of the set, maximum size of the set is n, so I get a bound of log. So basically what it's going to show is that the algorithm cost A is less than or equal to log n times the optimal solution, which is the coefficient response. Okay, so
But we don't have opt, right? We have to multiply it with.
what do you mean we don't have opt? We don't have to have opt. What are we saying here? We're saying take the optimal solution, whatever it might be. Its cost must be. You must be able to express its cost in this manner. So I don't care what it is. I'm saying that no matter what the optimal solution is, I must pay at least this much. Or this divided by h. That's a lower bound. Then I reason with respect to my lower bound. Remember, we never actually reason with respect to opt. We reason with respect to the lower bound. What I'm showing here is that opt is greater than equal to this big thing divided by h. But the algorithm was equal to that big thing. So lower before that. So this kind of sleight of hand is very common in approximation algorithms, which again makes them a little bit tricky to design. You have to find this device, this object, that is based on the structure of your algorithm. Like for vertex cover, we had the matching. For this, we have these weights. And by the way, these are more related than and that device allows you to reason about optimal solution. I will hand out a note that tells you how to prove this. I think while it's interesting to see how this works, it's it'll take a bit of trickery, and it's maybe not as useful to do that. So what you see here is that you get these different kinds of approximations depending on the problem. And in fact, like we can characterize problems as polynomial time or NP-complete, you can take problems and look at how well they can be approximated, or how it seems they can be approximated. Some problems seem hard, some problems seem easy, and so on. But as you're seeing, every problem I'm coming up with a completely different argument from scratch. I claimed I had this nice, oh, there's a lower bound, here's an upper bound, do this kind of stuff. But in every problem, I had to think very hard with something completely different. And that's kind of frustrating. Because for any new problem, how do I even know where to start? And it turns out there is a kind of generic way to design approximations for problems, especially for hard problems. I think problems are actually hard. For problems that are polynomial time and you want better approximations, it gets a little bit more complicated. And that involves this thing called linear programming. That essentially you can take a problem, express it in terms of linear programming, and use that to get lower bounds and therefore reasonable quality of solution. And that's what we'll talk about next time. But we'll look at a very big hammer that can generically give you these kinds of lower bounds that we're constantly searching for, and then therefore allow you to reason about how good you are with respect to the optimal solution. Okay. All right. So I will see you all next week. If you have any questions.